I know that love is just for people, but what about the microscopic world? Do atoms meet and fall in love, just like a boy and girl? Now I know that atoms aren't people.
All right, it's kind of hard to man the tech and film all by myself here. Welcome to the ionic bonding part of Chapter 6, Honors Test Hints. So we're looking at ionic and metallic bonding in this section. And if you look over the test hints that we have printed for you, you'll see that I still have the whole bonding chapter for the honors book all in one. But we are going to split this into two parts. And we're going to start with what is technically the second half with ionic and metallic bonding this year. And we're looking at test hints 31 through 52. 31 through 52 on your Chapter 6 Honors Test Hints page. And that's going to correspond to test questions 1 through 22. So it's a short test. This half of the chapter is really a little bit less than half. So let's get started. Your first test hint, it says to explain or describe how an ionic bond forms. And you'll remember that we started in this chapter comparing ionically bonded things to covalently bonded things. And we did a lab where we melted different solids and we tested their solubility and we did conductivity. And we were testing both ionic and covalent substances, not metallic though, just to get a sense of how those substances differ in their properties. Well, they really differ in how the bond forms. And the key for ionic bonding, of course, is transfer of valence electrons. I'm just writing the transfer of electrons. Of course, you know it's the valence electrons that are so crucial in bonding. And when electrons are transferred, they're transferred from a metal to a nonmetal. So we've also been talking about it that way, metal to nonmetal. And in that process, ions form. The metal ions are called cations, and the nonmetal ions are called anions. Now, once we know that cations and anions are formed, we know that they have a charge. Of course, our cations are positive. We're sure about that. And our anions are negative. So positive and negative, and that creates an electrostatic attraction. So when we get our crystals of ionic substances built up, we have alternating negative, positive, and so on, because opposite charges attract. Really pretty straightforward. Test hint number 2 says explain why purely ionic bonds cannot occur. Why can't we have something with 100% ionic character? That's a simple calculation where we're taking the electronegativity of the nonmetal minus the metal divided by the nonmetal's electronegativity, and we're getting somewhere over 50% ionic character. Well, we don't have a metal, say sodium, giving up its valence electron in its outer shell over to something like chlorine. Very common example. Chlorine needs one valence electron to fill up its octet. And you know, the sodium just doesn't give that electron and wander off somewhere else. Once that electron is transferred, that sodium ion with a positive charge forms, and the chloride ion with a negative charge forms, and there's that attraction between them, and they are bonded that way. So we're never going to get something that's 100% ionic character, although we'll have ionic compounds with very high percent ionic characters. Test hint number 33, which is question 3, describe the types of bonding for each range of percent ionic character. So you have this chart in your notes, but I'll jot it down again for you here. For those, you know, like maybe 2 students who use this as their notes. Of course, the rest of my students are so dedicated and motivated that they've been pouring through the notes, they've been looking at their assignments, they've been watching the videos on Moodle, all over it. I am so proud of you. So each range of percent ionic character. Let's go back to that equation. I'm abbreviating percent IC. We have that x sub A minus x sub B divided by x sub A times 100. That's B. And that's the element with the higher electronegativity minus the one with the lower electronegativity divide by the higher one, times 100. If we end up with an answer that's in the 0 to 5% range, that's a covalent bond, and it's one with very little difference in electronegativity. That happens to be a non-polar covalent bond. Because we're doing the ionic chapter, or the ionic section first, we haven't touched too much on this, but we will be comparing, and you'll certainly see a lot more about nonpolar and polar covalent in the next part of the chapter. Something in the 5 to 50% range is polar covalent, and 50% to 100% is what we classify as an ionic bond. Now these are just guidelines. I don't want you to think that, you know, something, well, it's above 50%, it's got to be ionic. That's not always true. And we can have some things that are maybe, 47, 48, 49% that are still ionic, and as long as it's made with a metal and a non-metal. So look at the kinds of atoms that are involved there also. And we could have something a little bit above 50% that is still technically polar covalent because it's made of two non-metals, but they are quite far apart on the periodic table and quite far apart in their electronegativity. Moving on to test hint number 4. Identify the pair of elements with the greatest or least percent ionic character when you are given examples. Well, you need to know your trend for electronegativity that we learned back in the periodic table chapter. And you can really just tell this from the difference. Here are some examples of what answers to this question might look like. How about potassium K versus bromine Br? Or maybe H versus Br, hydrogen versus bromine. Or how about a bromine-bromine bond? Or even a Cl Br bond. Well, I almost gave them to you in order here. Potassium is way over on the left side of the periodic table. It's a metal. It's an alkali metal. Bromine is a halogen. They are very far apart in their electronegativity, and that is definitely going to be an ionic bond. I can tell because it's a metal with a non-metal. I can also tell by following the trend for electronegativity that we know went to the right and up in the periodic table. Or I could just flip my periodic table over and look at the actual electronegativity value, since I've got that sitting right in front of me while I'm taking this test. Hydrogen and bromine have a difference in their electronegativity. It's a pretty decent difference. That is going to be a polar covalent bond. Bromine-bromine is a covalent bond because it's two nonmetals, but that's going to have 0 difference in electronegativity. This bromine atom has the same electronegativity as that bromine atom. That is going to be a nonpolar bond, and it has the least difference in electronegativity. So our potassium to bromine had the most in this example so far. Bromine to bromine has the least. And then a chlorine-bromine bond, they're two different elements with two different electronegativities, and they're pretty close on the periodic table. They're going to be polar. That'll be a polar covalent bond, but maybe just slightly polar. Okay? Test hint number 5. 35, question number 5. Calculate the percent ionic character and identify the type of bond. So, move the slider back a little bit and